This is lecture number 39 of the course ME314 Fluid Mechanics 2, and the third lecture of this week. We already have talked about drag coefficients, different values of drag coefficients, and calculating drag in previous lectures. In today's lectures, we will talk about the drag coefficients for vehicles. So we will look into the history, how in automotive the drag coefficients over the years is reduced. We will look into this drag resistance as well as the rolling resistance, and we will work out the power which is actually required to drive the vehicle, which depends upon the sum of the drag forces and the forces overcoming the rolling resistance. We will look into one problem related with the drag and rolling resistance, and in the end, we will look into the ways by which we can reduce drag in vehicles. So this is historically in 1930s this fight. This vehicle had a drag coefficient, average drag coefficient of 0.6 in this Merc Volkswagen had 0.46, and over the years we see this nowadays in the modern shape, this tear down shapes in Ford and in this Mercedes in the order of 0.3. So this is how historically the drag coefficient in different vehicles has been improved, and we can see this picture is over the years. So in 20s it was 0.8, in 40s 0.7, in 70s it was 0.5, and in 80s 0.45, and recently nowadays is order of 0.3. So where usually the drag coefficients for recently cars, different type depending upon different types of vehicles, and we're talking about passenger cars. So it is an order of 0.3 nowadays, and for special vehicles like concept cars, it can go up to 0.1 and 0.15 order of that. The development, obviously, this over the years, what the drag coefficient has dropped in this whole century is by different reasons. One of the reason is highways have been formed, and there is a requirement of vehicles to be run at high speeds, because we already have seen the drag force is square of the speed. So and the drag force becomes significant once vehicle speed is some high value, and on highways in some countries in the world, on highways there is no speed limit. So that actually forces manufacturers to, because once you are moving at a very high speed, then the drag force becomes significant. So that is one of the factor which actually demands which forces manufacturers to improve the drag coefficient. Secondly, different metal forming technologies have improved, so we can have those monocoque designs for vehicles, and so that the body can become more streamlined, and that actually has an impact too. And the gasoline price also forces, especially in Europe, the gasoline prices used to be 3 times the price in US. So there was a more R&D work taking place in Europe for drag reduction, because the gasoline price were much higher due to different taxes imposed in Europe compared with the US. So there would be several instigators for over the years taken place for reducing the drag coefficients. If we look at a car having a mass m, which is accelerating with an acceleration a on a level road, so the propulsive power, or the driving force, which is the force which is required to propel the vehicle, If we just consider the two type of forces, one is the rolling resistance, which is due to the contact friction between the tire and the road, and that rolling resistance would be depending upon the magnitude of the friction coefficient that is present between the road and the tire. And the second force, which is the resistive force, which is against the drive force, is the drag force. So if you just balance the forces, so the drive force minus all the resistive forces like the resisting force, rolling resistance, and the drag force, the net force is responsible for accelerating the vehicle in this direction to the rightward. So this is the mg is the weight of the vehicle, and a is the acceleration to which the vehicle is traversing to the right. In case of constant speed of a vehicle, if on the level road vehicle is moving at a constant speed, then the acceleration would be zero. So I just substitute acceleration 0 in this formula. So I end up with the drive force would be the sum of the rolling resistance plus the drag force. So that would be the formula for calculating the drag force. And we know a lot about the drag force in the earlier lectures. Now we talk about the rolling resistance. As we know, the rolling resistance depends upon how the contact area and the pressure distribution that takes place at the contact point between road and tire, and different grips of tires and different road surfaces would have different friction, and so this contribute into rolling resistance. So in simple form, we define that the rolling resistance can be calculated if we know the normal reaction that takes place between the contact surface of the tire and the road, and it would be directly proportional to this coefficient of rolling resistance, so which is, we call it mu r. So if we know the weight, because weight is acting downwards, so the normal reaction would be equal to the weight. So we can calculate this rolling resistance, which will be mu r times m times g, because the normal force is actually just the weight of the vehicle. Because this normal reaction is taking place not at one wheel but at all four wheels. So this would be the formula for calculating the rolling resistance. If we are interested in calculating the power, we know the power is the driving force times the velocity. So once the car is moving at a constant speed, and the speed of the car is v car, is actually the car of the speed of the car, then the power required to drive the car would be the driving force times the speed of the car. So as we know, the driving force is a sum. When the vehicle is moving at a constant speed, then the driving force would be the sum of the rolling resistance plus the drag force. So if you multiply that together, we'll be able to calculate the power. And if the speed unit of speed is in meters per second, and the unit of force is in Newton, then newtons into meter would be the joules, and the joules per second would be the watts. So that would be the unit of power, that would be in watts. Just take an example. If we have a bicyclist, bicycle rider having a mass of 70 kg, so actually it's a combination of the mass of the cycle as well as the rider, which supplies a power of 300 watt while riding into a headwind. 3 meters per second would be the wind speed. The frontal area of the cyclist and the bicycle is given as 3.9 square feet, and so in meters square it would be 0.362 meters square, and the drag coefficient which is given here is 0.88, and the coefficient of rolling resistance is 0.0007. and the density of air is 1.2, we have to find out the speed of the cyclist. So headwind is actually once you are moving against the wind, that wind is actually called as headwind. And if you are moving, the wind is moving from the in the direction in which you are traversing, that is actually called as tailwind. So that is actually, and the speed of the wind which is actually crossing the rider, then it actually is called as crosswind. So these terminologies are used in with any vehicle: crosswind, headwind, and tailwind. So here we have a tailwind. So we know the wind velocity is 3 meters per second. So I have used a minus sign because I am assuming the cyclist is moving in the positive direction. So wind is opposite to the direction of the cyclist. We know the concept of the relative velocity. So the cyclist is moving, there is a wind, so there would be the speed of the cyclist relative to the wind, and this is how I have written the relative velocity v of the cyclist relative to the wind. So this slash is representing that this is actually the relative velocity. So here relative to the wind, that is actually the upstream velocity. So that is actually the cyclist velocity minus the wind velocity. So if you substitute numbers like so relative velocity would be the cyclist velocity plus the wind velocity, which is 3 meters per second. So that is because wind is moving and cyclist is also moving in the opposite direction. So it means the relative velocity would be the cyclist velocity plus the 3 meters per second. We know the data given for drag coefficient, frontal area is given for both cyclist and rider, cycle and rider, and the friction coefficient is given. So we can easily calculate the rolling resistance, which is coefficient of rolling resistance times this normal reactions, and normal reaction would be the weight of the cycle and the cyclist. So the weight is mg, and mass is 70 kg, the g is 9.81. So there would be a rolling resistance of 4.81 Newton. And then we can calculate the drag force. So the drag force here is the drag coefficients times the dynamic pressure times the area. So area is 0.362 meters square is given, and here the square of the speed would be the relative speed of the cyclist relative to the wind, and so that would be the cyclist speed plus 3, that would be the relative speed. So take the square, and 1.2 is the density of air, and half is that multiplier, and drag coefficient given here is 0.88. So we have an expression for drag force. As we know, we don't know the cyclist speed. That is something we have to work out. As we know, the power is given here. So power is equals to the drag force times the velocity of the cycle. So we can substitute here these two expressions. We know the rolling resistance is 4.81 and the drag force is 0.19114 times Vc plus 3 whole square. So this is a non-linear equation, so we have to solve this equation. We can solve it using ease or by some spreadsheet. You can do that. For example, once your cyclist speed is 0, let's say, so 0 plus 3 and the whole thing would be, then the power comes out to be 0. So we just substitute different values of the cyclist speed, let's say 5 meters per second, and then see whether we are getting this 300. So at what value of Vc we will be getting power 300, that would be our answer. So this thing we can do it by using ease as well. So I will show it how we can do it on ease. So on ease, if you see that we have written that equation, that was our rolling resistance plus the drag force, and that V is actually, I've taken the velocity of the cyclist, so plus 3 whole square. If you can see the formatted equation, we can solve such nonlinear equations on ease as well. So this is the power we have written, 300 watts, and this is the rolling resistance, and this is the drag force, and multiplied by the speed of the cycle. So I will be able to calculate, write down this equation to solve, and I can see it in a formatted form. So it is Vc is the cycle speed. So only unknown in this equation is the Vc, which I can solve. I just click on the solve, I will be able to solve that. So I got the value of 9.12 is the speed which will satisfy that equation. On ease, there are so many other things we can do. Is for example, instead of one value of power, if let's say I just make it a power, and I go to make it a parametric table and just make it a 30 runs here, and select these two variables to be added here, and I got this table. So if I just make this table in such a manner that the speed of the cyclist varies from 0 to 15 meters per second, then I will be able to calculate the power. So I can plot that too. Simple. On x-axis this thing, and on y-axis this thing. So I will be able to plot that too. So it is I can see that how the cyclist speed, which is on the horizontal axis, and the power requirement to drive the cycle at that speed varies with. We can see that at 300 watt we can have 9.12 meters per second the speed is. So as I increase, we can see that the power varies non-linear with the cycle speed. So that is very important because of this non-linear term of the drag force, which is square of the velocity. So that's why we have this non-linear behavior. And you can see, let's say, moving from 10 meters to 11 meters per second. So there is a huge requirement of power because of this non-linear behavior. And what we can do is, once we have a plot, what else we can do on this plot is, let's say we want to have the equation which to be curve fitted. So I can have that equation, let's say I have a polynomial 3 order equation. I can fit that equation. So I can see the stats of those equations. So its R value is 100%. It means it is complete correlation. Correlation coefficient is an order of 100%, and I can see these. I can just plot on that, and you can see it in bigger format. If just make it 18 size, so I can see that would be the equation actually, that is relating the cycle speed versus power. So curve fitting is also can be done quite easily on ease. So for this problem, we have the power and cycle speed relationship, and we have seen that there is a non-linear behavior. So the power requirement varies non-linearly with the speed of the cyclist. And if we see that the rolling resistance, which is a linear function of the speed, vehicle speed is plotted on the horizontal axis, and the drag force, or this the air is due to that air resistance, that is a non-linear function. And if you add the rolling resistance and the air resistance, as we have seen in the problem, we will be able to draw this power versus speed curve. And we can see that this power and speed is non-linearly related, and it is very important that this drag force is non-linear, is just because of the square of the velocity. So if you have started with a speed of, let's say, 50 miles per hour and move to 60 miles, so the power requirement increases quite sharply. So Higher speed means more power consumption, and so in order to be more economical and at lesser speeds you are more safe, the vehicle is more safe, then we need to choose the optimum speed at which the power, the power requirement is minimum, or something which further increase in the speed result into considerable power requirement, so which is something we have to avoid. And in trucks, as you see, this fairing, we already have talked about, external part of plastic is used at different angles so that the body becomes streamlined and reduces the gap as well, in order to improve the drag coefficient. And once you improve the drag coefficient, this air resistance, which is a non-linear function, also improves, and in this way we'll be able to reduce the power consumption. One of the tasks on wind tunnel performed for a vehicle like sedan shape body with the 3/8 scale model, and we can see the pressure distribution here. The pressure coefficient is plotted, and you can see this bold line is something without a deck lip, so deck lip is not there, and with deck lip you can see this as magnitude of this negative pressure has reduced on the rear side. So once the pressure difference is reduced, then this pressure distribution reduces the drag as well. So one can see that this can optimize this requirement of drag. But as you know, the once you have a DAC, this it is not just taking care of this pressure distribution, is not just taking care of the drag, but it is taking care of the lift as well. So in such cases, this DAC actually DAC lift provides the negative lift. So lift is always upward, negative lift means downward force, and at high speed the vehicle stability and control can be improved. What you call it, a traction improvement can be done because of those negative lift. And even though this lift provides drag, but actually it provides this negative lift as well. So we have to make some trade-off between the drag and the lift, and depending upon the speed requirement and the shape of the body. So this study has suggested that the overall drag reduction, greatest reduction, is when your lip height is about 20 millimeter. So all these wind tunnel study helps in improving the design, and we can do the drag reduction in cars as well. For drag coefficient less than 0.3 would require efforts in design as well as in workmanship. For example, the underside of the most car is very rough, like axle, wheels, muffler, fuel tank, shock absorbers, and these are all the equipments which the surface roughness is very high. So it is there is a friction drag part available. So one way to reduce this is to add a panel to the bottom of the car. But bringing the panel at the bottom of the car reduces the ground clearance, and since muffler is also place which is actually dissipating heat to the environment, so it actually affects on the heat transfer as well. And we know that there are some interior airflow system for engine cooling is there, so whatever the air coming from the front is helps in so this so we need to take into an account the effect of the airflow system which is used for cooling as well. So once you are trying to reduce the drag, but there are some other constraints as well. Similarly, there are some external features like, so So these exterior features such as the mirrors, antennas, and other surface protrusions, they also contribute to the drag as well. And we know the formula for the drag coefficient is if you reduce the frontal area, your drag coefficient reduces. So once you reduce your drag coefficient, obviously fuel consumption also reduced. We already have seen the drafting helps in reducing the drag because you're following a vehicle and you come into the low pressure region, so the pressure distribution over the over your vehicle changes, which reduces the drag and eventually helps in fuel consumption. Similarly, the windows which the rolling resistance can be so on a highway when you are moving with the high speed, the drag is considerable. So once your windows are open, that actually increases the drag. So which one of the way is close the windows and we can switch on the AC. So the power given to an AC would be less than what is power which is consumed due to the drag force. So these are the measures which can help us in reducing the drags. In locomotives nowadays, the high speed trains are moving with very high speed, so there is a considerable drag. For example, of this height of the cabin edge, this streamlined zone is of a length of 3.25 of this height. So there is a considerable efforts in design to be made in order to make the shape of the body streamlined so that it reduces the drag. And since these speed trains on either side, on the upstream side as well as on the downstream sides, it has to be aerodynamic. And obviously the drag coefficient will be varying at different values. So for 1/76 scale or 1/40 scale or a full scale, you have different values of at different Reynolds numbers, and you have total drag coefficient is order of 1.4 something, and the largely it is due to the shape part. The friction part is negligibly small. So that's why the shape of the body is more crucial in such design. So in all vehicles, aircrafts, rails, and ground vehicles, in every vehicle, the drag at high speed plays an important role, and it has to be considered in the design as well.